Today's lesson focuses on a concept called Hess's law. Hess's law is used as a method to calculate the enthalpy of certain reactions that are difficult to carry out in a lab setting. So we're going to use some other methods in which to calculate an overall enthalpy for a particular reaction. And the image that we have here is showing you kind of an analogy of Hess's law. If we were all starting at the bottom of this mountain and we had to get up to the top, we would expel energy or release energy in order to do that. If we could go straight up the hill, okay, we would release a certain amount of energy. But if we took a different path and we kind of took our time and maybe carried it out over several days, we wouldn't exert as much energy in the same amount of time, but over the time period, we should be exerting the exact same amount of energy. And this is what Hess's law is dealing with. Instead of us going straight from reactants to products, we're going to create some side products and side reactions and eventually get to those products over a different pathway or different amount of time. So why do we use Hess's law in certain applications? Well, there are many reactions whose energy changes cannot be measured in our lab for a variety of reasons. They're either too slow, okay, so they take too long and we can't actually carry out the reaction in, a day or a couple of days, or maybe they're too extreme or too uncontrollable, fast or dangerous. I think of dynamite. If you wanted to blow up some dynamite, which is a combustion reaction, who would do that, okay, in a lab setting? So there are certain reactions that we just can't do, but we still need to isolate those enthalpy changes and figure out the amount of energy that is either released or absorbed. So in certain cases like that, the enthalpy change can be determined using math, simple math, and logical deduction. And as I mentioned on the previous slide, enthalpy is what we call a state function. So it only depends on the initial and final state of the reactants and products, not on the pathway that is taken. So we can use small subreactions in Hess's law to determine the overall enthalpy of one reaction. And it's good to note too that the enthalpy change that accompanies any chemical change is independent of the route or pathway taken. And based on all of these ideas, we can then come up with a heat summation. Summation means an addition of small subreactions to calculate the enthalpy for an overall. Here's just a little diagram showing you that if you wanted to figure out the enthalpy of reaction A to B, but you couldn't carry it out in the lab setting, you could take some different approaches. Maybe you maybe you react A and you come up with some sort of intermediates that will eventually give you B. Then you could take this enthalpy of that reaction, that enthalpy there, add them up, and it should equal the overall that we are intending. Otherwise, you could also take a couple of different approaches. Here's one reaction, two reactions, three to get to the same final set of products. Either way, all of these pathways should add up to the overall. So Hess's law, the definition is kind of wordy, but if two or more thermochemical equations can be added together to produce an overall equation, the sum, okay, so we're adding here, we're going to be adding the sum of the enthalpy terms of the chemical equations equals the enthalpy change of the overall. Let's do an example. So here are two thermochemical equations. I always like to number them. So this is 1 and 2. And we know each of these equations in terms of their enthalpy value. And what we want to do is we want to combine these two subreactions to give us the enthalpy change for this overall right here. So we don't know what this enthalpy is, but we can determine it using these subreactions up here. So how do we do this? Well, here's our overall again. So we always are keeping our eye on the overall equation. And when we look at these subreactions, and here's reaction number 1 right here, I'm really only interested in substances in this first reaction that I see in the overall. Okay, so sometimes you're going to notice that there'll be intermediates in these sub-reactions that are not in the overall, so we don't really care about them. Sometimes we'll notice something like oxygen. I need oxygen in the overall, but I see oxygen in this reaction and in the second. So when you'll see a substance multiple times over several sub-reactions, leave it alone. Okay, don't go there. So what I'm going to do is I'm going to zero in on this carbon. Okay, I need carbon in the overall reaction, and I see it right here, and I don't see it in this second one. Okay, it's not there. And because it's not there, I know that if I match up these carbons, then I'm going to be able to solve this problem, even though I'm not really focusing on these guys over here. And that's okay. You'll see how this all will work out. So when we are trying to match up terms or trying to match up, elements or products, a couple things have to happen. We have to make sure that they are on the correct side of the equation. And this one is carbon is on the reactant side in the overall, and it's also on the reactant side in the sub-reaction. The other thing I have to make sure matches up is the coefficients that are here. So I have a coefficient of 1 in this reaction, and I have a coefficient of 1 in this sub-reaction. So I'm actually going to just leave this entire sub-reaction alone. And I'm not going to worry about these guys right now, okay? So let's go down to reaction 2. What is in reaction 2? So which reactant or product is in reaction 2 that I need in this overall up here? And again, we have seen CO, okay, there's CO, so there's something that I can maybe focus on. Here's oxygen, but again, I have oxygen in the other reaction, so I'm leaving it alone. And trust me on that, it usually will work out. You don't even need to bother with it. I see CO2 in this sub-reaction, but I don't see CO2 up here. It's not there. So I'm not going to focus on that because I don't even know what to do with it. So I'm going to take this carbon monoxide that's in my sub-reaction, and I am going to match it to the carbon monoxide in the overall. And already you should be able to see a bit of an issue. I need this carbon monoxide to be on the product side. And over here, it's on the reactant side. And I also have too much of it. I don't want 2 moles of it in the overall. I just need 1 mole of it. So what we can do in chemistry is make the assumption that every chemical reaction in theory is reversible. And if we assume that, what we can do is we can flip this reaction totally around. So I can take my reactants and I can flip them over to products, and my products I can flip over to reactants. When I do that, I have to change the enthalpy sign. Okay, this particular subreaction is telling me it's exothermic. If I flip it around, it's going to be endothermic, and so I've got to change the sign on it. I also can, scale up or scale down the coefficients. So I don't want to have 2 moles of carbon monoxide. That's fine. I'm going to divide the whole thing by a factor of 2 so that I match up the coefficient over here to get a value of 1. Okay, so let's show you how I would expect to see a solution for Hess's law. Here's your overall, and then we're going to take these sub-reactions. So when we take a sub-reaction and we are manipulating it, we usually put a little prime symbol. That's that little dash that I put after the reaction. Remember that we didn't do anything to that first reaction. We didn't need to do anything. So usually what we do is to indicate that, we say that we multiply everything by a factor of 1. That's telling everyone that you're not multiplying it by any other coefficient, and you're also not flipping it. So we're just going to rewrite that original reaction again and include the states. Sometimes with Hess's law problems, the states will change, and that will cause some details to be observed. So it's always good to rewrite everything exactly. And so keep this enthalpy change exactly the same. Okay, nothing is changing there at all. Now, with that second reaction, this is where we're going to call it, 2' is the way that we would write that. Remember that we said we needed to flip the reaction and divide everything by a factor of 2. So to do that, you can say here, you're going to divide everything by 2, and the flip is going to be coming evident by a negative sign. So you can say you can divide by -2, or you can say you're going to multiply by -1/2. Either of those is acceptable. And that half is still implying that we're dividing everything by a factor of 2. So remember, you got to flip everything. CO2 was on the product side. It had a factor of 2. We're dividing everything by a factor of 2, and we're flipping it. So it's now going to go on the reactant side. Carbon monoxide now becomes on the product side, and only a coefficient of 1 because we're dividing everything by 2. With oxygen, we only had a coefficient of 1. If I divide by 2, I now have a half of an oxygen. And now don't forget with your enthalpy, right? We're flipping everything. So I now have a positive enthalpy. This is very important. And when I divide that enthalpy value by a factor of 2, I get 283. And make sure you keep that decimal place, right? We're going to be adding up everything. Make sure it's there. Okay. So now what we do is we go through and we either add up reactants and products, right, on either side of the reaction arrow into one overall. Anything that we see on opposite sides can get canceled out. So notice right here, I've got CO2 on the product side, 1 mole of it. And then I have CO2 on the reactant side. Because they're on opposite sides and there's the same amount, they cancel right out. Over here, I have half of an oxygen on the product side, and over here I have 1 mole of oxygen on the reactant side. So they don't totally cancel out, but they do get subtracted off. So this half is going to be gone, and I would be left with a half of a mole here on the reactant side. And then I usually box out, what is left over that matches the overall. Okay, and here's my carbon monoxide that matches the overall there. So we just rewrite everything nice and tidy. There's my half of O2. So normally we don't use we don't use fractions in chemistry, but we do here. Okay, so we do in Hess's law and in the next lesson as well. And then we are adding up these enthalpies, right? This is Hess's law of heat summation. So be careful. You've got a negative sign up here and you've got a positive sign right there. Make sure that you're punching that into your calculator. Overall, this reaction is exothermic at -110.5 kilojoules. Here's another example that we'll go through. So we want to know this enthalpy for the reaction of 4 ammonias plus 5 moles of oxygen, creating 4 moles of nitrogen monoxide and 6 moles of water. And again, for whatever reason, we don't want to combust ammonia in the lab setting. Fair enough. So what we're going to do is use these 3 sub-reactions that you see here, and we're going to manipulate them to match the overall and figure out the enthalpy of my reaction. So when we manipulate our sub-reactions, you don't have to do them in order. Okay, it doesn't really matter which way you do it. So what we're going to do here is we're going to set this up and we're going to kind of like go down the list, right, of the reactants and products and match everything. So we're going to first focus on ammonia. And so I want to go into my sub-reactions and I want to find ammonia. There it is right there. And notice that I only see it once. So I see it in this reaction. If I can focus on this reaction and match it up, okay, so I need it on the reactant side. I also need double the mole value of it. I can address that. So we're going to multiply the entire subreaction by -2. Negative, remember, implies that we're flipping it. There's the flip right there. But we also are multiplying everything by a factor of 2 as well. And so this is why our enthalpy values change. And so we'll notice here my coefficients change as well as I flip the overall reaction. Now let's go down the list over here. Let's focus on oxygen. So when I focus on oxygen, I notice that I see oxygen in 2 sub-reactions. And so we don't deal with it, okay? It's gonna work out in the end. Pardon me. Just skip it. Let's focus on the first product, which is nitrogen monoxide. So where do I see nitrogen monoxide? Only once, right here. Okay, there it is right there. Now, the good news is it's on the same side, so I don't need to flip it, but I don't have enough of it. So we're going to take everything and we're going to multiply everything by a factor of 2 to match up those coefficients. And again, you got to do it to all the coefficients, all the enthalpy values as well. And so we'll see that down here. Lastly is water. So I find water right here. I only have 2 moles of it. I need 6 moles. It's on the proper side. That's good news. I got to multiply everything by a factor of 3, which we've done down here. You rewrite those equations again. And when you do, you'll be able to cancel out any terms on opposite sides. So again, there's 2 nitrogen and 2 nitrogen on the opposite side. Cancel them. There's 6 hydrogen and 6 hydrogen on opposite sides. Cancel them. There's my 4 ammonia that I need. Here are the 2 waters, but they're on the same side. So we add them up, right? 2 plus 3 is 5, works out. There's my nitrogen monoxide. I now have 4 moles of it. There's my water. I now have 6 moles of it. And remember, you've got to add everything now in terms of the enthalpies, and you should get a value of negative 906.3. Is the reaction endo or exo? Again, keep track of those negative and positive signs. They're so important. Negative is telling us overall it's an endothermic reaction. Give this last example a try in your notebook. So here is your overall. We want to know what is the enthalpy of this reaction. We don't know what that is. And then here are your 3 subreactions, and go through the exercise. Focus on substances that you see in the overall. Try to match them up. Don't forget to apply that to your enthalpy values, and you should get an answer of negative 137 kilojoules.